how to do the Ice Rink Lab online. So several of you emailed saying you were a little confused on what to do and how to get started. So that's pretty normal. This is a difficult problem because unlike a lot of the problems we do in class that are like one equation, one step to solve, and sometimes we have two equations we use to solve for a problem, this one uses more than what we've been used to using up till this point. So it's understandable why we might be getting confused with this. So let's get started. So basically the idea is there's a video of a person sliding on ice to the left. So we do not know what the initial velocity is. That is a mystery to us at this moment. And the person is sliding down here and they come to a stop. So if they come to a stop, that means that V final is 0 meters per second. Okay, so we are trying to find ultimately the coefficient of friction of the ice and the person. So that's what we're trying to solve for. So how are we going to do that? There's a few equations we've learned. We've learned that the force of friction is the coefficient of friction times normal force. So that would be kind of the most natural way to get started. The problem is we don't know what normal force is because we don't know anything about the person. And before we go too much further, I'm going to draw a free body diagram of the forces on the person because I think that's going to be really helpful for us to visualize this. So my person gets reduced to a dot when I'm making a free body diagram. The first force that's acting on him, or it doesn't really matter the order, but I always put gravity first. Gravity always points down, so force of gravity. And then the person's not moving in the up and down direction because there is a normal force that is preventing the person from falling through the earth, and that's the ground pushing back up. And these are going to be equal and opposite forces. Now, once the person starts sliding, right, they're moving to the left, they're moving this direction, but they're slowing down, which means that the friction is happening in this way. So the friction is moving that direction, and that is causing them to slow down. So I'm going to draw my friction force this way. Okay, so that's going to become useful for us in a moment. So we know from looking at this diagram that my normal force is going to be the same as force of gravity. And we did learn an equation for force of gravity in class, and that was force of gravity equals mass times the acceleration due to gravity on Earth, which we know is 9.81. We also learned Newton's second law, which was acceleration equals F net divided by mass. So all of that is going to become helpful for us in a moment. So if we go back to our free body diagram, what is F net? Well, let's think about that. Normal force and force of gravity, they cancel each other out. So the only thing that's left is actually F net equals our force of friction. That's the only unbalanced force that's happening on our person. So that's going to come helpful for us a little bit later down the road when we're trying to solve for force of friction. So we're going to need to tie in that Newton's second law equation there. Okay, but we don't know acceleration, right? But we do know that V final is 0. We know in the video we can measure a distance, right? We can measure a distance that the person is sliding. We can measure the time the person is sliding. So these are things we can measure in the video to help us find acceleration. Now, I told you there were two ways to find acceleration, because there are. So I'm going to scroll down and just talk about how do we find acceleration. So how do I find acceleration? Okay, so we could use a kinematic equation, or we could do a graph. I'm going to go over both of those methods, but the first one I'm going to go over is graphing. Okay, so there is one way to do this by graphing, and the other one is using a kinematic equations. So if you were to go the graphing route, you would need to make a table where you're measuring the time and the distance and then the velocity. And we've done this many times before in lab, actually. So you would, I don't know what you want to use for your time interval, 0.2, 0.4, I don't know. You pick what you want your time intervals to be, the distance traveled, whatnot. You're going to make a distance versus time graph, and it is probably going to look something like this, kind of like an upside down parabola. Then to make a velocity versus time graph, what you have to do, if you remember using the linear function, and you had to find the slope between 2 points, and then you had to find the slope between those 2 points and the slope between so on and so forth, and you put those values into the velocity table, and then you would get a velocity graph that would hopefully give you a line, okay? So if you need help, reference the, what lab did we do this in? The acceleration lab. You did the same thing. And we've done it a few times in the lab, so that's one way to do that. But how do we get the acceleration? For this graph, the slope of the velocity versus time graph is acceleration. Ta-da! So you have to remember that. And why is that? Because velocity over time is the rate of velocity. It's the rate at which velocity is changing, which is the same thing as acceleration. So that's one way to find the acceleration, but you don't have to do it that way. It's just one option. The second option is to use the kinematic equations. And I thought this was going to be easier, to be honest. So I kind of encouraged my classes to do it this way. And then in office hours, when we actually sat down to do it, I realized it was a little bit more complicated than I originally thought, which is fine. It's still doable. But it does require a little bit math. So these are the kinematic equations we're familiar with. If you remember from our picture up above, we don't know what V initial is, but we do know that V final is 0. And if you notice, every equation has V initial in it and acceleration. So we can't actually use any of these equations because we don't know what V initial is. So we have to be a little bit more creative. There is something called average velocity, right? We learned this back in September, and average velocity is simply distance divided by time, right? That's in our reference table. It was the very first equation we learned. We also know that average velocity is also the same as V initial plus V final divided by 2, simply just taking the average of those two velocities. Well, this actually does work out for us because V final is 0, right? This is 0. So if this is 0, this goes away. So then I can rewrite this to be V average equals V initial divided by 2. And if you notice, we have a V average and a V average. We can set those two equations equal to each other. So V initial over 2 equals distance divided by time. Solve for V initial, so we're going to multiply by 2 on both sides, and we get 2D over T is V initial. Once we get V initial, voila, we can use our kinematic equations. It doesn't, at this point, doesn't matter which one you use, because we know V final, we know V initial, we know time, and we know distance. So pick your favorite kinematic equation to do, solve for acceleration, and you will get your acceleration. Now, what if your acceleration is negative? Does that make sense for our scenario? I'm going to come back up here. So you're probably going to get a negative acceleration. And that makes sense because friction is slowing it down. By default, we picked the left direction to be positive. We didn't define that at the beginning, but we measure the distance. We're assuming distance is 0 here, and whatever our distance is there. So we picked the left to be positive, and the acceleration's in that opposite direction, so it's negative. Okay, great. So we have solved for acceleration, whether you use the graph or those equations. Next, we need to figure out, so we know acceleration, we don't know mass, and we know that F net is actually the same as force of friction. So what I'm going to do here is I'm going to pick a different color. So A equals, instead of F net, I'm going to put friction, force of friction, over mass. And then we know that force of friction is actually this equation. So I can rewrite this. So now it's A equals coefficient of friction times normal force divided by m. Okay, well that kind of helps us because ultimately we're trying to solve for this value, but we still don't know what F normal force is. But we know that F normal equals force of gravity, and we know that force of gravity equals mass times gravity, which is this equation here, which means normal force also equals mass times gravity. So we're going to substitute this in for that, and when we do that, we get A equals mu times mass times gravity divided by mass. And when we do that, guess what? Mass cancels out. We never needed to know the mass this whole time. So we get our acceleration equals the coefficient times gravity. And from here, you can solve for the coefficient, and that would be your answer. So how do you know if your answer is correct? Well, this is just a ballpark, but you remember this table from class. We know that rubber on ice is roughly about 0.15 for the approximate coefficient of friction. So your number should be, whatever you get for your coefficient should be somewhere between 0 and 1, but it probably should be a little closer to 0, because if you notice, this number is, pretty close to 0, more close to 0 than it is 1. And it's, because ice is slippery, it's going to be a smaller decimal value. So you should get something close to 0, and go ahead and round to the 100th for your final answer. Okay, so that's how you do this problem. You're going to use the same process to solve for the Prius on the ice. What is tricky about the Prius on the ice is that it's hard to see when the brakes are applied. You have to look carefully at the front wheel tires. When the front wheel tires stop spinning, it happens about a little over halfway of it driving across the rink. That's when the brakes are on, and you can read in the thing about it. They have anti-lock brakes, so they behave a little bit differently, but it's when the wheels first stop spinning. You might want to move it like frame by frame to see exactly when that front tire stops spinning, and then that's going to be your indication. Okay, so I hope I covered everything that you need to know to be able to do this. Oh, one last thing. So I mentioned that the acceleration is going to be negative. That's fine. When you solve for the coefficient, if you take the negative value of gravity, so negative 9.81, those two negatives cancel out and you'll get a positive number. If that confuses you, just take the absolute value of your final answer and that would be fine. All right, so I hope this video recorded well, and I'm going to upload it. And yeah, hopefully this helps.